sometimes finding a solution to a differential equation is almost impossible. When that's the case, we can use a graphical solution to take a differential expression and find a general shape, and then kind of estimate a particular solution based on that general shape. So if we take a look at an expression for a differential equation, it kind of takes on the form of the differential expression is a function of sometimes just variable x, sometimes just variable y, or sometimes both variables. And this is nothing more than basically, since it is a differential expression, it's a dy dx. It's nothing more than the slope of the tangent line to the function. At that particular point. So if we can then create almost a grid system to show all of the values of those tangent lines at each particular point, then we can get an idea of what that we can get an idea of the general shape of the solution, and then also graph a particular solution through a specific coordinate. So if we take a look at that, when we take a look at that differential expression, which is just no more than the slope of the tangent line, we get what we call a slope field. And so the slope field then is a graphical representation of that differential equation. And so here, if we take a look at this example, here we have a differential expression. It's a function of both x and y. And so we're just going to find the value of those slopes at each particular point. So at the point negative 4, 2, the value of the slope would then be negative 4 minus 2, that would be negative 6. At the next point, negative 2, 0, the slope would be negative 2 minus 0, which would be negative 2. At the next coordinate, 0, 4, we'd have 0 minus 4, which would be a negative 4. The slope here would be 2 minus 4, which would be a negative 2. The slope here would be 4 minus 6, which would be a negative 2. And the slope here would be 8 minus 8, which would be 0. So if we take a look at those locations, minus 4, 2 would be minus 1, 2, 3, 4, up 2. That would be this point right here. So that short blue line represents a slope of negative 6. At minus 2, 0, which is right here, the slope of this blue line is about negative 2. At 0, 4, that is 1, 2, 3, 4, that's right here. The slope of this short blue line is negative 4. At 2, 4, so 1, 2, 1, 2, 3, 4, right there. The slope of this short blue line is negative 2. At 4, 6, so 1, 2, 3, 4, up 6. The slope of that short blue line is also negative 2. So if you look at those two lines, they're parallel, those two tangent lines. At 8, 8, so over 8, up 2, 4, 6, 8, 8, that's this point right here. We can see the slope of that short blue line is 0. And so all of these short blue lines are nothing more than the slope of the tangent line, the line tangent to the function at that point. The graph here is a slope field for the differential equation dy dx equals 1/3 x squared minus 1/2 x. And so if we kind of identify the tick marks here, 5, 6, 7, 8, 9. So the tick marks are here 10, by 10. So it's a standard graph window for like a TI-84 or something. And so we're talking about sketching the slope field through the point 1, 1. So that point is about this location here. And if we then draw the slope, draw the solution that passes through that point, basically all we're trying to do is kind of match the value of the slope of the tangent line, and so we're kind of following that contour of that slope field as we go through the point on the slope field. So if we can kind of estimate the values of the slope here, we look like we have something that is about like that. So if we look at that kind of, that shape kind of tends to look like a cubic. And of course, if we would get the particular solution to this, we'd have to integrate that. And if this is a quadratic and this is an expression for the differential, then integrating that would be a cubic. So if we integrated y prime, that would require integrating this, which is easy enough to do. So if we just take a look at this, integrating this gets us 1/9 x cubed, and integrating this gets us 1/4 x squared plus c. And so as you can see, we do have a cubic here. And we can substitute 1, 1 into this expression and actually get the particular solution. So this one isn't terribly difficult to find a particular solution for. So we put in the point 1, 1, and we can evaluate for c here. So we have 1 equals 1/9 minus 1/4. And evaluating for c then would get us 1/9 is 4/36 minus 9/36, so that's a minus 5/36. And then adding that to both sides gets us 41/36 for our constant of integration. So the function, at least to the best of my sketching abilities here in green, is 1/3 x, excuse me, I said that wrong, is 1/9, I'm reading from this line here, x cubed minus 1/4 x squared plus 41/36. Euler's method is a numerical approach, and it allows you to approximate the value of a particular solution at a point on the graph. And so if we look at the idea of Euler's method, it's really what we would call a linear approximation. And so what we do is, as we assign values for x, we use a linear method here to approximate the next value for x and y, or the next value for y, based on the step here, h. And basically the step h here is determined to be small enough so that this tangent line doesn't deviate too far from the actual function. And so if we look at this carefully enough, we can see that really this is nothing more than the expression of a linear equation. We have a slope here, right here, which is the f, x sub 0, y sub 0, and we have h, which is that step here, the delta x, so to speak. And so we really have kind of a y equals mx plus b form to this linear approximation, and that's how we That's what we use to determine this new value for y. So we would start out here at x sub 0. We would, and that would be this point here, and we would take the slope of the line going through x sub 0, which is this value here, and when we take that slope and multiply it by h, all that's determining is the height here that we moved up. And so here is our next value for y. And so if you notice, this tangent line here leads to this value. And then this becomes our new starting point to repeat the process. And as you can see, we have these lines then that closely follow the exact curve, but are not exactly on the curve, which is why we do call this a linear approximation, because this linear approximation is made up of very small line segments from one point to the next. In this example, we're going to perform several Euler's method calculations to approximate the values, to approximate the solution of this differential equation here, y prime equals 0.5x times y. We're going to start at 1. We're going to start at 0, 1. So our starting point here is 0, 1. And we're going to go 10 steps with a step of 1/10. So really what we're going to do is we're going to start at 0 and we should end up at 1, something. And we will get then an approximate value for the function at 1 after we go through these steps. So here we are, we're starting out at 0, 1, and we want to know what the slope of the tangent line through 0.01 is. So this is that short blue line that would appear on your slope field. So we go ahead and plug it in. 0.5 times 0 times 1 is 0. So the slope of that line is 0. And so if that slope is 0, then we can go ahead and approximate the new value at 1/10 over. And so the new value for x is 1/10. The new value for y is 1 plus the slope times the step. So the slope of 0, step of 1, so the new value of y is 1. So if you can picture then, and the picture's kind of down below here, we started at 0 and we had a slope of 0, so we moved over to 0.1. So there's our next point in Euler's method. And that point is 0.1, 1. And so now we're going to use that set of points to determine our next slope, and then consequently our new value for y. And so go ahead and finding the new slope here. We have 0.5 times x, which is 0.1, times y, which is 1. And so the new value of our slope here is there we go. Okay, so the new value for our slope here is 0.5 times 0.1 times 1. I'll just put that on there for kicks and giggles. And so our new slope is 0.05. And then there we go. Our new value for x2, let's see, we started at 0.1. We moved 0.1, so our new value for x2 is 0.2. Our new value for y2 is y sub 1, which is 1, plus the slope, which is 0.05, times the step, which is 0.1. So our new value for y is 1 plus 0.05 times 0.1, which would get us 1.005. Okay, so there's our new value for y2. So those numbers come down here. And become our x and our y that we start out with. So our new slope then is 0.5 times x times y. So times 0.2 times 1.005. And so our new value for the slope is 0.5 times 0.2 times 1.005, which is, as you can see, our slope is now getting just a little bit steeper. This is 1.005, or excuse me, I said that wrong, 0.1005. And so our new x3 is 0.2 plus 0.1, which is 0.3. And our new y3 is 1.005 plus our slope of 0.1005 times our step of 0.1. So our new y3 is 1.005 plus 0.1005 times 0.1. And so our new y3 is 1.01505. And so we keep doing this. I'm going to have to do this a bunch more times here. So our x3 is 0.3, our y3 is 1.01505. And then we go ahead and calculate our slope again. So our slope is going to be 0.5 times x times y. So times 0.3 times 1.01505. And so if we come over here and calculate that, we have 0.5 times 0.3 times 1.01505. And that means our slope here, again getting steeper, it's now 0.15226, I'm going to call it. So I'm starting to take enough decimal places, but not all of them. And so our x4 now is 0.3 plus 0.1, which is 0.4. And our y4 now is 1.01505 plus the slope, which is 0.15226, times the step, which is 0.1. And so that's, in fact, I'm going to do a little shortcut here because I have the slope right here. So I'm going to come back to the calculator and I'm just going to go times 0.1 so I don't have to, so I can take all the decimal places with me and not have to retype it. And then I'm going to go plus 1.01505. And so we have a new value of 1.030, I'm going to call it 0303 for my new value for y. So there's my new value for y. My new value for x is 0.4. I'm going to go ahead and calculate my new slope. 0.5 times 0.4 times 1.0303. And when I calculate that, I'm going to kind of play the same trick over here. I've got the value of y, so I'm just going to go ahead and go times 0.4, that's the value for x, and then times 0.5 times 0.5 to get an exact value for that new slope. As you can see, the slope continues to get steeper. It's 0.206. I'm going to call it 0606, even though there's more significant figures there. Our x5 is 0.4 plus 1, plus 0.1, which is 0.5. And then, as you can see, I'm kind of playing a trick with the calculator here, where I'm not writing down all the significant figures, but I'm definitely using them in the calculation, and I'm gonna keep continuing to do that. So we have 1.0303 plus the slope, which is 0.20606 times 0.1, the step. And so I'm going to come back over here to the calculator. I've got the exact value for my slope. I'm going to multiply it by the 0.1. That's my step. And then I'm going to add in my old value. Here's where the rounding comes in. So I'm going to have to round that to that decimal for the old value. So that new value for y is now 1.05091. So at this point, I'm at 0.5, and I'm at a new value of 1.05091, and I could continue at this point, but I think we're just going to kind of scroll down and look at that just to see where we are at 0.5. So at 0.5, so here's 0.2, here's 0.4, so this is 0.5 right here. So as you can see, we're starting to have a deviation from the actual. This is the actual function itself right here. Okay, that's the actual function itself. And as you can see, as we connect these linear approximations that we get when we do Euler's method, these linear approximations are starting to deviate from that actual function. Oops, that was a bad line. Those linear approximations are starting to deviate from that actual function in a pretty significant manner now. And again, the slopes of those are nothing more than what you would see on that slope field that we were working with just in the previous examples. So we're right here now. If we continue that all the way for the next 5 steps to get all the way over to an x value of 1, you can see we are substantially, this is 1 comma something we would get for Euler's method, and we are substantially below the actual value here at 1 of the function itself, using those linear approximations known as Euler's method. And just an aside, if you have a TI-84, there is a program that you can load onto the TI-94 in your program window, and it will automatically do these calculations, print out all the values to fill in your table, and draw the graph on a graph page for you. And I do have that program. If you would like that program, just come over and see me, and I can get that loaded onto your calculator for you.